Hello students. Now let us see the Davison-Germer experiment, and this experiment is useful to study the atomic structure and the spectrum of the hydrogen atom. How it is also related with this explanation of the wavelength. Now in this experiment the basic thought is that now there are two different waves reflected in between the in the nickel crystal. So different atomic layer of nickel crystal will have a fixed phase difference. Now what happens after reflection of these waves will interfere either constructively or destructively, producing a specific pattern. In Davison-Germer experiment, the scattering of slow-moving electrons by reflection from the surface of nickel crystal under the influence of potential difference of V due to the electrical field of the strength V into E acting on the electron of charge E, and the electron emerges out with a uniform velocity. Now in this experiment, from the surface of the nickel, now the electron emerges out. Now on that emerged electron is having some velocity c units, having charge E. So the kinetic velocity 1 by 2 m.c. square acquired by the electron due to the electric field shall be equal to the electric force. That is equal to the electric force. So that is mathematically we can say that 1 by 2 m.c. square is equal to VE. So if you want to calculate this velocity c, so it is get calculated by c is equal to under root of 2 VE upon m. So multiplying by m on both sides, we will get this equation mc is equal to under root of 2m VE. But what happens according to the de Broglie relationship? Already we know that mc is equal to h upon lambda. mc is equal to h upon lambda, and so if we put this in the above equation or we compare the equations, we get next equation, that is lambda is equal to under root of h square upon 2m into lambda is equal to under root of h square upon 2m into VE. So the beam of electron of definite wavelength we get diffracted from the nickel crystal with the angle of diffraction theta and graduated circular scale. So what happens according to the Bragg's diffraction equation, the wavelength of diffraction, diffracted radiation is given by the equation lambda is equal to d sin theta, where here d is the constant. For nickel, d is equal to 2.15. So by substituting the value, we get the wavelength of electron wave. So by using above equation, we are able to find out the wavelength of the electron wave. So that is get carried out by using this schematic representation of Davison-Germer experiment. Here in this is a schematic diagram for this Davison-Germer experiment, and from this experiment, so this is the source of the light, battery current is provided and the electron beam is bombarded on the surface of the nickel crystal, and we get a diffraction pattern, that is the electrons are ejected with a specific wavelength, and that wavelength we have seen given by the equation above. We had seen that equation lambda is equal to under root of a square upon 2m into VE by using this. So this is the schematic diagram. Now let us see a very important principle, that is Heisenberg's uncertainty principle. As today we know that this principle is useful to find out the probability of electron in the orbital. So Heisenberg uncertainty principle states that one cannot depict the exact position and momentum or velocity of subatomic particle like electron at a same instant. That means in electron there are the there is a centrally placed nucleus, and around that in the orbit electrons are revolving. Now, according to the Heisenberg, there is a probability of finding the electron. That means we are not able to find out the exact position of that electron in the orbit, but at the instant there is a probability of finding the electron in that orbit. So mathematically it is get expressed that in delta x into p is greater than delta x into p is greater than or equal to h upon 4 pi. So here delta x is uncertainty, that is error in the position of the electron in the orbit, where delta p is the uncertainty of the error in the momentum of that electron. So delta x is a uncertainty error of a position of electron in the orbit, and here delta p is a uncertainty error in the momentum of that electron. So another way we can represent this equation as delta x into delta m into v greater than or equal to h upon 2 pi. Now the delta p is equal to delta m into v, and that value we put in this equation, that is value of this delta p we put in this equation, so we get this another equation. So delta p is equal to, here we have m into delta v. So here we can again say that delta x into delta x or delta v is greater than or equal to h upon 4 pi m. From these values we substitute in this equation, so we get this another equation, delta x or delta v is greater than or equal to h upon 4 pi. So the above equation, this equation is called as Heisenberg's uncertainty equation. This equation is called Heisenberg's uncertainty equation for the explanation of position of electron in the orbit. Whatever the uncertainty is there in the orbit, that is get explained by this equation. Now let us see the significance of this Heisenberg uncertainty principle. So what is the significance? First, the uncertainty principle is used to determine the definite path of the moving object. That moving object here is the electron in the orbit. So this principle explains or used to determine the definite path of moving object. So the fixed path of the object is found out by its position and velocity at various moments. We are able to find out the fixed path of the electron. Particularly we are concerning about the atom and atomic structure. So here in this case, in the centrally placed nucleus and in the orbit, we are the fixed path of this object, that means electron, is found out by the position of the electron and the velocity, or what we call momentum of that electron at a various moment. So if we know the position of an object, its velocity and the force acting on it at a particular instant, then we can find where the object could be at the same time later. So again, the uncertainty principle is not significant in daily life. So it is significant for certain specific cases, but in daily life this is not significant. Now let us see next a Schrödinger wave equation. Now the quantum mechanical model of an atom comes from the solution of the Schrödinger wave equation. Quantization of an electron energy in the requirement of the order to solve this equation. This model is generally deals with the probability of finding the electron around the nucleus. So the time independent reduced form of the Schrödinger equation is, this is whatever this equation is a time independent reduced form of this Schrödinger equation, that is Hamilton operator into the psi is equal to E into the psi. Here this delta H hyphen is a Hamilton operator or partial double diffraction, and this capital E is a total energy of the system, and this psi function is the wave function of the system under observation. That this system may be the single electron or atom or the molecule. So Schrodinger explained the probability of finding the electron using this Schrodinger wave equation, and that equation is d square psi upon dx square plus d square psi upon dy square d square psi upon dz square plus 8 pi square m divided by s square into e minus v into psi is equal to 0. Now, by solving this equation, we get the three coordinates, the value on the three coordinate x, y, z coordinate value, which gives us the probability of location of the electron in various orbits. So, if we want to find out the position of that electron in the orbit, which is revolving around the nucleus, so by solving above equation or this equation, we are able to find out a probable position or location of the electron in various orbits. So, that's why the Schrodinger wave equation, we can say that it is useful for finding out the probability of the electron in the orbit. So, these three variables are the three quantum numbers. That means the position of electron in the orbit is explained by this equation, but it is in the form of a different three quantum numbers. And these quantum numbers are principal quantum number, azimuthal quantum number, magnetic quantum number, and fourth quantum number comes later. From that we today know that that spin quantum number, what we say, from these spectroscopic techniques, and it is called as a spin quantum number, as we know. So, these four quantum numbers gives us a exact location of the electron in the atom. That means all the quantum numbers, what is we can say a principal quantum number, which is denoted by the symbol small n, azimuthal quantum number, and next is the magnetic quantum number m, and next azimuthal quantum number, that is get denoted by the symbol L, and magnetic quantum number denoted by the symbol small m, and spin quantum number is explained by the small s. These are the symbols for the quantum numbers, and all these quantum numbers all together gives us a exact location of the electron in the orbit. So, quantum numbers are very important to explain the position of electron in the orbit. Now, let us see what is orbit and the quantum number in the brief. So, orbital, what is orbital? As we know today that orbital is what? It is a distribution or probability of finding the electron in a particular path of the three-dimensional space around the nucleus, and that particular space around the nucleus in three dimension, we can say it is a orbit. So, orbit is a three-dimensional space around the nucleus in which the electrons are there, and that fixed path in three dimension, that space is called as a orbit. So, quantum number, let us see the quantum number. Now, quantum number, what is quantum number? It is a set of numbers. These numbers are useful to detect the probability of location and the state of the electron in the atom. Now, where the electrons are situated in the orbit, what is the position of electron and what is the state of the electron, or what is the momentum of electron, that we can able to say by using the set of numbers, that is principal quantum number, azimuthal quantum number, magnetic quantum number, and the spin quantum number. All these set of quantum numbers, these are the quantum numbers which gives us a location or probability of the electron. So, there are four types of the number, as we see. The first number is a principal quantum number. Now, as I had said that principal quantum number is denoted by the symbol n. Small n is the symbol by which we are able to find out or it is a quantum number which is useful to locate the position of the electron. So, it can have any position or whole number excluding 0. It has values 1, 2, 3, 4. Quantum number is n, that is principal quantum number, it is never 0. So, it determines the energy level in which the electron is present. Now, what happens? Principal quantum number determines the energy level of the cell in which electron is present, and the value of n represents the corresponding cell. If n is equal to 1, 2, 3, 4, now it represents K, L, M, N cell respectively as shown in the below figure. This is the figure. These are the different cells. N is equal to 1, N is equal to 2. K cell, L cell, M cell. In that N is equal to 1. And it regards the energy level. It tells about the information of the energy present, energy of that particular orbital. So energy of an electron in an atom is given by this equation. Whatever the energy of electron present in orbit, that is given by En is equal to minus 13.6 into Z square upon N square electron volt. So by this equation, we are able to find out or explain the energy of electron in the orbit. So this is the schematic representation of the cell in the atom. Now this value of N is also useful to calculate the maximum number of electrons in that cell. That means how much electrons are there in the cell. That N, that is principal quantum number, gives us about idea about the number of electrons present in that particular cell. So whatever the maximum electrons present in that particular cell is given by the equation 2n square. So by using this 2n square, we are able to find out the number of electrons present in that particular cell. So as we know, here n is the principal quantum number. The size of an orbital or the radius of an orbital increases with increase in the value of n. So as value of n increases, the radius of the atom also goes on increases because there is an introduction of the extra cell in the orbit. That means this is nucleus and this is orbit, and if this is a K cell, so it has an n is equal to 1, and we increase the value of n. That means there is an introduction of the another cell, as we know. I am drawing this. This is nucleus. So K cell, n is equal to 1, n is equal to 2, n is equal to 3, and so on. And as this value of n increases, the size of or radius, what we can say, radius of an atom, or we can say orbit, increases, and hence the size of atom also increases. So the size and radius of orbital increases with increase in value of n, and it is given by this equation. Rn is equal to 0.529 into n square divided by a angstrom unit. By this equation, we are able to predict the radius of orbital. Now let us see this another quantum number that is called as a azimuthal quantum number, given by the symbol small l. Now this azimuthal quantum number determines the angular momentum of an electron, and it is denoted by the symbol L, as we saw. So particularly, principal quantum number gives us a radius of orbit and energy of the orbit or the cell. So this azimuthal quantum number is important to find out the angular momentum of electron present in the orbit, and it is denoted by the symbol. Now it also gives information about the subcell and the number of subcell present in the orbit. So value of L ranges from 0 to n minus 1. 0 to n minus 1, where, as we know, here n is the principal quantum number. So the L, that is azimuthal quantum number, have a number of values depending upon the principal quantum number. Now let us see the value of L gives us a subcell, as we seen, to which the electron belongs to, and it also gives the information about the shape of the orbital. Whatever the shape of the orbital, that is get determined by the azimuthal quantum number. So we know that the total number of subcell is equal to the number of cell. Total number of subcell is equal to the total number of cell. So the different subcell, that is orbitals, are designated by the first writing the value of n and then followed by the L. Whatever the different suborbitals present in the orbital are get designated by firstly the principal quantum number n, and then by it is get followed by the azimuthal quantum number L. So we will understand it by the examples given below. Now the cell number The number of subcell and maximum number of electron in subcell are well discussed, as we have here the chart by which we are able to find out the value of this principal quantum number, how the value of azimuthal quantum number is get determined. So if n is equal to 1, that is principal quantum number is 1, that means there is a k cell in the atom and it has subcell. That means this L is azimuthal quantum number. So L is equal to 1 subcell, because we have the formula we have seen above it, that is n 0 to n minus 1, that these are the values of 1. So we submit the value of this n is equal to 1. So 1 minus 1 is equal to 0. So if n is equal to 1, L has only one subcell. That means that orbit has only one subcell. Here the value is get calculated n by 1. We are putting here value of n is equal to 1. So we have value of L is equal to 0. Then 1s orbital is present in the orbit, that is in the cell, k cell. There is a 1s orbital with a 2 electron. As we know, the number of electrons 2n square, in the orbital are 2 electrons. S orbital occupies 2 electrons. In second cell, we are talking about the second cell that has a principal quantum number n is equal to 2. So it is a L cell. If L is equal to 2, it is L cell, and here the L is equal to 2. There are 2 subcells in the which get denoted by the azimuthal quantum number. That means when we put the value of n2 in this equation, we get value of L is equal to, we can put 0 and 1. Here we have this 2 minus 1, 1. That means we have the value 0 to 1. That means there are 2 values of L. That means there are 2 orbitals present in that L cell. That is L is equal to 0 and L is equal to 1. That means 2s orbital and 2 p orbitals are there. As we know, each p orbital, that is px, py, pz, has a capacity of 2 electrons and totally 6 electrons are there in the p orbital. So as so on, if L is equal to 3, L is equal to 4, we are able to find out the number of orbitals present in the subcell, and that is get denoted by the azimuthal quantum number L. Now let us see next quantum number, magnetic quantum number. Now in magnetic quantum number is a third quantum number on the so it is a third quantum number on the list between spin and azimuthal quantum number. Spin and azimuthal quantum number, and it is designated by the symbol, as I highlighted, it is denoted by the symbol M. If split the subcell, we split the subcell SPTF into the individual orbits and place the electron in one of them. It defines the orientation in the space of a given orbital of particular energy and the shape. That means this orbital, what we say, magnetic quantum number, gives us a particular energy and a shape. Thus, the energy value of M has 2L plus 1 value. That means this value of M has 2L plus 1 value, which gives us a number of orbitals, and it gives a value ranges from minus L to plus L. So depending upon the value of azimuthal quantum number, we have the value of magnetic quantum number including 0, and it is well explained. Now let us see the values of this magnetic constant number. If orbital is S, that means L is equal to 0. L is equal to 0 when n is equal to 1. So this orbital, their number of orbitals present are 1. By the formula 2L plus 1, we put here value of L 0. So 0 into 2, 0. We get a 1 orbital is there, and that is, we know the S orbital is there, and magnetic quantum number has minus L, 0 and plus L values. Here values are 0, and as there is a S orbital, there are 2 electrons. If p orbital L is equal to 1, there are number of 3 orbitals, and we have in the p, px, py and pz, that means values are -1, 0 and +1, because here L is equal to 1. If L is equal to 2, there is a presence of d orbital. That means d orbital have 5 subcells, and 5 subcells, these are the dxy, dyz, dzx, dx square, y square and dz square. So we have L is equal to 2, then the value of this magnetic quantum number is -2, -1, 0, +1 and 2, and total 5 subcells are there and each of capacity 2, then we have there 10 electrons in the d orbital. Likewise, here L is equal to 3 for this f orbital, and so number of orbitals are 7. So the name and shape of the orbitals are very complex, that is f orbital have very complex shape. So it has, if we have this azimuthal quantum number is equal to 3, then the value of this magnetic quantum number, what we can say is 3, -2, -1, 0, +1, +2, 3. That is value is in between -3 to +t. And there are 5 subcells, means each of the 2 electrons, 7 subcells are there, and each subcell has a capacity of 2 electrons, then means there are total 14 electrons in the f orbital. So by this way, the magnetic quantum number gives us a values of these different orbitals, that is value ranges between these depending upon the azimuthal quantum number. Now last quantum number that we can say, that is spin quantum number. The spin quantum number has a symbol small s, and it describes the angular momentum of an electron. An electron spins around the axis. It has both angular momentum and orbital angular momentum. Because of angular momentum is a vector, the spin quantum number s has both magnitude, that means 1/2, and the direction plus or the minus, that is it is plus 1/2 or minus 1/2. So an electron rotates its own axis either by clockwise. If electron rotates in clockwise direction, then value is plus 1/2, and if it is in the anti-clockwise direction, the value of this spin quantum number is minus 1/2. Now let us see what is the importance of this last point, is the quantum numbers. As we know, the quantum numbers are important because they can use to determine the electronic configuration of an atom and probable location of electron around the nucleus. Whatever the location of electron there in the orbit, we are able to predict by using these quantum numbers, as we had seen it also previously. The number of the quantum numbers are also used to understand the other characteristic of atom. Which characteristic? That means ionization energy and atomic radius. If we know the exact position at the instant in the orbit, that is exact position of electron in the orbit and momentum of the electron, and by using these quantum numbers we are also able to find out the radius, then we are also able to find out the ionization energy. So by using these quantum numbers, we are able to find out the exact position, radius and ionization energy of that atom or the electron. So by these theories, we are able to understand the structure of atom. So this is enough for today. Enjoy the lecture. Thank you very much.